Welcome to Unit 7, Video 4, Electron Configuration. By the end of this video, you should know how to draw an orbital diagram for an atom or ion in its ground state. You should know how to write an electron configuration for an atom or an ion in its ground state using its position on the periodic table. And you should know how to recognize an electron configuration for an atom or ion in its excited state. There are two ways to represent the arrangement of electrons in an atom. The first is with an orbital diagram. An orbital diagram uses arrows to represent electrons and boxes to represent orbitals. So here you can see three boxes in a row representing the three p orbitals in the 3p sublevel. Each of these arrows represents an electron, so here we have 4 electrons in the 3p sublevel. We can also use an electron configuration, which uses letters, numbers, and superscripts, and looks like this. In this case, the big numbers represent the principal energy level. So the 1, the 2, that's n equals 1, n equals 2, n equals 3. The letters represent the sublevel, or the shapes of the orbitals. So here we have the 1s sublevel. And the superscripts represent the number of electrons in that sublevel. So this tells us there are 2 electrons in the 1s sublevel. Likewise, here we have 4 electrons in the 3p sublevel. There are some rules that govern the way in which electrons occupy the energy levels in an atom. The first is the Aufbau principle. Aufbau is German for building up. This tells us that the electrons are added one at a time to the lowest available energy orbital first. In other words, you won't fill a higher orbital until lower orbitals are completely full. Then we have the Pauli exclusion principle. This tells us that orbitals can hold up to 2 electrons and that they must have opposite spins. We represent opposite spins by arrows pointing in opposite directions. This implies that the electrons have opposite spins. And finally, there's Hund's rule. Hund's rule tells us that we must maximize unpaired electrons by putting 1 electron in each orbital within a sublevel before doubling any up. For instance, here's a sublevel with 5 orbitals. Since it's a sublevel with 5 orbitals, it must be a d sublevel. If we're filling this sublevel, we first must put 1 electron with the same spin in each orbital of this sublevel before putting 2 in any orbital. So now that we know the rules, let's practice drawing some orbital diagrams. Here's a template that will help you draw these orbital diagrams. Let's start with an orbital diagram for carbon. Carbon has 6 electrons, so I'm going to put 2 in the 1s orbital. Then I'm going to put 2 in the 2s orbital. That's 4 electrons, so I have 2 more. 1 each is going to go in the first 2 orbitals of the 2p sublevel. Since they have the same spin, they should both be pointing in the same direction. It doesn't matter if that direction is up or down. From here, we can write an electron configuration. It would be 1s2, 2s2, 2p2. Let's try a different element. This time, let's do neon. Neon has 10 electrons. I already have 2 in the 1s, 2 in the 2s, 2 in the 2p from the previous one, so that's 6. I have 4 more electrons. So I can put 1 more in the 3rd orbital of the 2p sublevel. Now I'm going to start doubling up. So I put 3 more in the 2p sublevel. My electron configuration here would be 1s2, 2s2, 2p6. Electron configurations actually correspond directly to the position of an element on the periodic table, and you should be able to write the electron configuration for any element simply given its position on the periodic table. So how does this work? Well, the number of the largest principal energy level that it contains electrons is given by the period number. So in other words, elements in the first period will have electrons in the n equals 1 principal energy level. Elements in the second period will have electrons in the first principal energy level and the second principal energy level. Elements in the third period will have electrons in the first principal energy, the second principal energy level, and the third principal energy level, and so on and so forth. So that tells us what our last principal energy level should be in our electron configuration. From here, we need to know which sublevels are occupied in the atom. We do this by using blocks on the periodic table. Notice this periodic table here has been divided into blocks. We have the S block over here. Notice the S block also includes helium, so you can kind of sneak that in over here by hydrogen when you're thinking about the S block. So the elements lying in the S block will have electron configurations that end with electrons in an S sublevel. Then we have elements in the P block. Elements in the P block will have electron configurations that end with electrons in the P sublevel. Then we have the D block. Elements in the D block will have electron configurations that end with electrons in the D sublevel. Notice, though, that there's some weirdness here. Notice that we have, in the fourth period, a 3D sublevel. It actually turns out that the 4s orbital fills before the 3d orbitals. So you'll have to remember that the period rule works with the exception of the fact that the D block is essentially bumped down one level. So after 4s, you get 3d, then 4p. Then 5s, then 4d, then 5p, then 6s, then 5d, then 6p. And this corresponds to the filling order of orbitals. It so happens that d orbitals tend to fill after the s orbital of the next principal energy level, because they're lower in energy. And finally, we have the F block. Elements in the F block will have electron configurations that end with electrons in an F sublevel. We won't look much at elements with F block electrons because they're generally very large elements. Finally, we can determine the number of electrons in that last sublevel by determining how far into the block the element lies. For instance, take a look at this periodic table. Notice that all the elements in the first column of the S block have one electron at the end of their electron configuration. Here, all the elements in the second column have two electrons at the end of their electron configuration. Again, moving over to the P block, notice all of the first column of the P block ends with a 1 electron in its configuration. Likewise, skipping over to, say, the fourth, 1, 2, 3, 4, the fourth column, all of these guys have 4 electrons at the end of their electron configuration. You might also notice that there are a couple of exceptions down here where we start going out of order. Don't worry about them. There are some strange exceptions to electron configurations, but you're not responsible for knowing those. So let's try putting all of these pieces together. Let's say I want to write an electron configuration for nitrogen, element number 7. I know that nitrogen has completely filled the 1s orbital, so I'm going to say 1s2. I know it's completely filled the 2s orbital, so I'm going to say 2s2. And I know that its electron configuration must end with something in the 2p sublevel because it's in the P block in the second period. And I know that its electron configuration has to end with 1, 2, 3, since it's 3 over in the P block. So our electron configuration for nitrogen is 1s2, 2s2, 2p3. Notice if we add 3, 2, and 2, we get 7, which is the correct number of electrons. Let's try another larger element. Let's go with germanium, element number 32. Here, we know that the 1s sublevel is completely full. We know that the 2s sublevel is completely full. We know that the 2p sublevel is completely full, and the 3s level is completely full. We know that the 3p level is completely full. We know that the 4s level is completely full, and we know that the 3d level is completely full. Remember, we get a 3d after the 4s. So we know that it must end in the 4p sublevel. And we know that it must be 4p2 because it's the second one into that block. Add up your electrons and you should end up with 32. Finally, there's a shortcut for writing electron configurations. We can abbreviate part of the electron configuration by using the nearest noble gas. Noble gases are this last column of the periodic table, the last period there. They're kind of special in their electron configurations because their electron configurations completely fill up each sublevel that electrons occupy. So for instance, let's write an abbreviated electron configuration for magnesium. Notice magnesium is just after neon on the periodic table. Neon is element 10, magnesium is element 12. You have to use the nearest noble gas that comes before the element you're looking at. So argon wouldn't work for magnesium. Neon is closer. Since magnesium begins with 1s2, 2s2, 2p6, just like neon, we can use neon to take the place of that portion, giving us magnesium equals neon 3s2. Looking at the periodic table, this is super easy because we know we can write in neon, and then we know our electron configuration must end with 3s2 because magnesium is the second element in the third period in the s block. Now it's time to try some on your own. Pause the video here and try writing electron configurations for each of these elements. You may choose to write the abbreviated form or the full form, although notice for Mg2+, you may not write an abbreviated form. You'll see why if you try. When you come back, I'll display the answers. Welcome back. Here's what you should have gotten. Notice I've written the extended version first and the abbreviated version after. It doesn't matter which you chose to do. That brings us to our last point, excited versus ground states. Recall that when an electron is excited, it moves up one or more energy levels. So here's the ground state electron configuration for an element. Test yourself and see if you can figure out which element. If we excite an electron moves from a lower energy level to a higher energy level. In this case, an electron has moved from the 3s sublevel to the 3p sublevel. We know this is in its excited state because we have an unfilled orbital below the highest filled orbital. There are many possible excited states. Anytime you have an electron moving from a lower energy level to a higher energy level, it's an excited state. So here's another possibility. An electron here has moved from the 2p sublevel to the 3p sublevel, a larger jump. That brings us to the end of this video. Let's review our goals. First, we learned how to draw an orbital diagram for an atom or an ion in its ground state, using arrows to represent electrons and boxes to represent orbitals. Then we learned how to write an electron configuration for an atom or ion in its ground state using its position on the periodic table. Then we learned how to recognize an electron configuration for an atom or ion in its excited state.